thank you very much for the kind introduction, Alexandra. It's a pleasure to be with you today and have the opportunity to present some of our research on oromucosal drug delivery systems. I thought I would first talk a little bit about the site we are delivering to. There are several obstacles that we need to be aware of. So we will go through a little bit on the saliva flow, the mucin and the mucus as a barrier, the oral epithelium, how to increase residence time in the oral cavity, and also when we deliver things in the mouth, we need to think about the taste perception. Then we will have a look at a few examples, and I will end with summarizing as some concluding remarks. So first of all, the oral cavity is very accessible. We use it all the time for eating, so it's easy accessible also for delivery of drug, and it's easy to apply dosage form, but also to remove it if necessary. And it can be non-invasive and does not require complex devices in order to deliver the drug in the oral cavity. We can use it for local and systemic therapy, and we have a relatively large surface area available, rich in blood supply, and we can potentially also obtain fast onset of action. And we all know about nitroglycerin that is given sublingually and gives a fast onset, and so this can be obtained. It's not necessarily so, but it can be obtained. Compared to the GI tract, there is low metabolic activity, and we can avoid the first pass metabolism. And there is also considerably lower variability as compared to the GI tract. So it can represent an alternative to the intestinal route, and in some cases also injections. But in order to be successful, especially for transmucosal drug delivery, we need to prolong the retention of the drug or dosage form on the oral mucosa in order to give time for the drug to pass over the barriers. So let's start looking at the site of the delivery. Oral cavity consists of both soft and hard tissue, and it's continuously bathed in saliva. So in the oral cavity, let's say oral mucosa, that includes the buccal mucosa, the sublingual mucosa, the gingival, the palatal, as well as the labial mucosa. And the surface area, you find different values in literature, and it depends whether you talk about the total surface area or the buccal surface area, but it is between 100 and 200 square centimeters, and the saliva film has been determined to be in adult humans around 0.07 to 0.1 millimeter. But the thickness will, of course, not be constant, and there is a continuous flow of saliva The basal values is in the order of magnitude of 0.2 to 0.4 milliliter per minute. It's increasing during stimulation, and that can be smell, eating, creating increased saliva flow, but also the saliva flow changes during the day. So during night there is a very low flow, and it peaks around afternoon. And totally, the total flow can vary also quite a lot, but it can be in the size range of half a liter to 1.2 liters. And it's influenced by so many factors. Also, the lack of saliva flow is a severe problem. And dry mouth, whether it's caused by as a side effect of drugs or radiation to the neck, or other reasons, it can severely impact people's quality of life. And my good colleague, Professor Marianne Hjort, she's working exactly in this field of saliva, what to do with dry mouth and how to develop products for relief of that. But we will talk about other types of drug delivery systems. The composition of saliva is mostly water. Then mucin is a very important component. Then there are different type of electrolytes, glucose, peptides, proteins, also presented as enzymes and immunoglobulins. There are nitrous products. There are microorganisms, and they are the composition can change, but these are the main components. pH is also changing, but there are buffering agents. The bicarbonates together with urea and the phosphates modulates the pH. It's a hypotonic fluid. That is, it starts out when it's secreted as an isotonic fluid, but during when it comes out of the glands and reaches the oral cavity, it is diluted with water, so it's a hypotonic fluid. And the main functions is to lubricate the mucosal tissue, to protect the mucosal tissue, to protect the teeth also during speaking and eating, and it has buffering actions, and it has a high clearance, so it clears out acidic products, for instance, that or it captures microorganisms, and it controls the oral health, and it is important for taste and also for the digestion of food. It starts already in the mouth. So I mentioned that mucins are important substances and part, even though they are in a low percentage, they in the saliva, they have a large impact. And mucins are a family of glucoproteins, and they range in molecular weight from 1,000 up to 40,000. They can either be membrane associated, as the one shown on this picture, or they are secreted. And this one, there has been approximately 21, something like that, genes coding for mucins. And MUC1, that is a transmembrane type of mucin that is present in the oral epithelium. And among the secreted mucins in saliva is MUC5B and MUC7. So they have a protein backbone, and they are glycosylated, and the glycosylation is quite high, up to 80% of the dry mass of the mucin is coming from the glycosylation, and glycosylation is also contributing the hydrophilic character. Between the different types of mucins, the glycosylation can vary, and it expands due to and hydrates well in saliva due to the hypotonic property of the low ionic strength of the saliva. As such, mucin is low soluble, has viscoelastic properties, and they are strongly adhesive. And I mentioned that they have a backbone. Oh, this figure is a bit blurry, but it has a protein backbone, and the sequence of proline, serine, and threonine is central, and they are marked here in the pink. They are also where the glycosylation is happening. In between, there are cysteine-rich parts which can form disulfide bonds with other mucins, and these sections not associated with oligosaccharides can form hydrophobic interactions, and these are together forming a mesh in a network with both covalently and non-covalently linked between mucin chains. Then the oligosaccharide compartments will also contribute to the viscoelastic properties of the mucin. And the pink monosaccharides that you can see on the edge here is sialic acid, which has a pKa around 2.6 and will be negatively charged around neutral pH. Also, sulfate groups on the N-acetyl galactosamine and the galactose will be negatively charged. So we can talk about hydrogen bonding and ionic bonding that can happen also with interact with the mucin. So mucus forms a complex hydrogel, and it's mostly the secreted mucins that are contributing to the hydrogel, and they are linking up with the membrane-associated mucins. The pore size can be altered and filter particles of the different sizes. And the pore size can be influenced by pH, for instance, and the ionic strength in the surrounding. And this creates a physical barrier. Also, interactions of molecules can happen with the mucins, and that can be, for instance, due to charges. When we look at the surface of the epithelium, there has been reports showing that there are structures on the epithelial surface called microplegia. And on top of these, I think it's quite interesting to see in electron microscopy here that there is a protrusion through the surface, and that they have shown that is the MUC1, one type of mucin that is associated to the epithelium. So MUC1 and MUC5B are forming together the mucous barrier. And if we look at a simple cartoon of the oral mucosa, we have the mucous layer on top with all the possibilities of interactions and filtering. Then we have the oral epithelium, which is supported by the basement membrane and lamina propria below. And however, if we want to study permeability of drugs in the oral cavity, we should not forget that the epithelium here is made of stratified squamous epithelium and not simple columnar epithelium, as we know from the GI tract. So the thickness of the epithelium, there are many layers of cells. It varies how thick it is depending on where in the oral cavity we look. So the buccal mucosa is thicker than the sublingual mucosa. A drug can pass transcellularly, but it can also pass paracellularly. There are very little tight junctions in the oral cavity, but there is a lipidic material between the cells. So to pass the paracellular route, it is not very easy, and it's mostly available for hydrophilic and phobic lipophilic compounds. So in order to increase the retention, as the mucosa is constantly flushed by saliva, and the mucous barrier is another barrier that the drug needs to pass through. We need to look for ways to increase the retention on the mucosa in order to have transmucosal drug delivery. And mucoadhesion could be one way, where a dosage form gets in touch with the mucous layer and it interacts with the mucous layer to remain on the mucous layer. And that can happen, for instance, by hydrophobic interactions. It can be disulfidic bonds. It can also be dipole interactions or negatively charges and hydrophobic interactions, and also a lot of other ways of interacting. It can be electrostatic interactions, it can be dehydration, it can be diffusion of a polymer into the mucin. Also mechanical interactions will happen. And then wetting is yet another theory of how the interaction happens. If we want to increase the residence time in the mouth, then of course we expose the taste buds and the taste receptors for experiencing the bad taste of the drug. And we have different, as you all know, we have different taste receptors and on different locations on the tongue. The bitter taste is in the back, the sweet and salty is towards the front, and the sour on the side. Many drugs are experienced as bitter tasting. And therefore, it might be necessary to mask the taste. And this can be done by numbing or blocking, for instance, the bitter receptors. Sodium chloride is a molecule that has some use as a bitter blocker. We can obscure the taste by increasing viscosity, or we can add sweeteners or flavors that covers up the bad taste. Another approach is to make modifications of the API to play with the solubility or making a prodrug. Another approach is to create a barrier around the drug, for instance, by using a cyclodextrin to create a barrier, or we can coat the drug with a lipophilic coating that is not quickly dissolving in the oral cavity. So there are ways to mask the taste. So we have now looked at a lot of challenges that needs to be overcome in order to deliver successfully drug to the oral cavity. The saliva flow and the clearance of the saliva, the mucous barrier, the taste perception. Also, we need to be aware that the primary activity of the mouth is eating, drinking, speaking. All this can come into conflict with drug delivery. There could be also adverse reactions, local irritation or sensitization, depending on the oral health situation also will have an impact. And then there is a limitation to both the molecular size and also it's probably most suitable for very potent drugs, which need quite low concentrations in order to have an action. So then I thought we can look at a few examples on which opportunities we have. And let's start out by looking at what the pharmacopoeia defines as oromucosal preparations. They say that they are intended for oral administration to the oral cavity and deliver active substance for local and systemic effect. Mucoadhesive preparation, they should retain in the oral cavity by adhesion to the mucosal epithelium and may modify systemic drug absorption at the site of application. And then something we should keep in mind is that for many oromucosal preparations, it is likely that some proportion of the active substance will be swallowed and may also be absorbed via the gastrointestinal tract. So even though we intend for transmucosal absorption in the mouth, it could very well also be swallowed. And oral dispersible formulations are quite often placed on the tongue, and they will disperse or disintegrate within very short period of time in the mouth. The USP says that it should disperse within 30 seconds. The European Pharmacopoeia says within 3 minutes. So, but the message is oral dispersible systems are supposed to fall apart and be soft and can easily be swallowed after a shorter period of time. Then both the buccal mucosa and the sublingual mucosa are often seen used for transmucosal delivery as well. So I thought I should present some results from our research on oral films. And we have looked at both disintegrating and more mucoadhesive systems. We will start out by looking at some very simple HPMC based films that were prepared by solvent casting and evaporation. And we used furosemide as the model drug. And it's not that poorly soluble. It is a BCS class 4 drug, but solubility is clearly dependent on pH. And we used hydroxypropyl beta-cyclodextrin to form inclusion complexes with regards to taste masking. But also it has some solubilizing contribution. So first, the flow curves of the polymer, they were not very much influenced by neither the addition of glycerol as a plasticizer nor the cyclodextrin as a taste masker. So this was also not expected that it would be highly affected, but that it was nice to see. Then films were casted and cut into single dose units, and we could see that thickness and the mass is correlated, not surprisingly, and also that when we included beta-cyclodextrin as a taste masking component, the film thickness, when we kept wet film thickness the same, the film thickness would increase, and the mass, and this was also not surprising. Then we characterize the mechanical properties, and they are useful since the films needs to be handled and they need not to be brittle. So our HPMC films, they were a little bit stronger than commercially available films, but the commercial reference here is made from a different polymer and probably a different preparation method also, but we kept it in as a comparison to see what range of properties are we talking about. So the films were a little bit stronger and a little bit more elastic, deforming. But it's important that they are not too brittle and cracks and breaks upon touching. So, so these values are quite okay. Then we looked at how hygroscopic is the film material and how are our films compared to commercial references. And we investigated that with dynamic vapor sorption, where we exposed the films for increasing and decreasing moisture level in 2 cycles, and measure the mass change. And the curves of the HPMC films, they increases more at 25 degrees than at 37 degrees. The pharmacopoeia defines all materials as hygroscopic if they are equilibrated at 80% relative humidity and take up more than 15% mass water. So both commercial films and our films clearly are on the hygroscopic side. They are easily wettable. The contact angles are here around 30, 35, and all below 90 degrees are wettable, but the lower is more wettable, and this correlates well with moisture absorption. Then we also looked at swelling and erosion, and since these are hydrophilic polymers, they will swell up quite a lot, and these 2 types of films showing an HPMC film and an HPMC film with a beta-cyclodextrin, they follow the same profile. They swells up approximately 3.5 times the original mass within a few seconds, and then it erodes gradually and is completely dissolved after 3-4 minutes in this setup. Then we collaborated with or had a visiting PhD student from Rome, and he had developed a millifluidic flow-through device where he has the film in a channel and pumps the fluid above the film. And he wanted to investigate an oral film in this setup. So we used the HPMC films and we compared the release in the microfluidic flow-through device with the standard USP setup, but we reduced the amount of volume to 500. These systems, they release the drug very fast, of course, but in the microfluidic environment, they are not exposed to that much liquid, which would be more realistic compared to what's in the oral cavity. And then the release will depend on the flow rate that is passing by. We used these HPMC films as matrices for adding nanoparticles into the films. And one of the aims of adding nanoparticles was to use them as a mean to mask the taste. And in this study that Martina did during her master thesis, we used coumarin 6, which is not a drug, it's a model substance. It's a lipophilic fluorescent marker that we used to substitute as a model for lipophilic drugs. The SLNs were made from lipoid S100 and polysorbate, and we used the design of experiment, a central composite design, to look at the effects on the size from the surfactant and lipid, and we obtained particles in the size range from 100 up to 150 approximately, and both the lipid and the surfactant had an impact, but the variation between the different formulations were not very large. All polydispersity indices were below 0.15, and the particles were physically stable for approximately, or we studied them over 4 months, and they were stable during that time. Since the SLNs are made from a phospholipid, we thought it might be, or we wondered whether they were really SLNs with a solid core, or they would be more liposome-like. So therefore, we tested also 2 different drugs, one more water-soluble drug, metronidazole, and one strongly lipophilic drug, clotrimazole. And we tried to load them into the same or a couple of formulations from the design. And we chose a low surfactant level because we didn't see the need for a lot of surfactants, as the particles were stable for 4 months. In size, we could see a difference between the 2 drugs, and there were also a difference in size between the amount of lipid used. Zeta potential were slightly negative or close to 0, but the stability for these particles are ensured by the surfactant on the surface. But then when we look at the drug encapsulation, we can see that very, very low amounts, practically none, were loaded into from the water-soluble drug. And around 50% encapsulation was obtained for the clotrimazole, the lipophilic drug. And well, this was not there was not done any optimization, so whether we could obtain higher drug encapsulation here was not studied. But we think that we can conclude that they are actually SLNs. And then we go back to the SLNs with coumarin, and they were loaded into HPMC films, and the films were a little bit thicker and a little bit heavier with particles than without, not to a significant level. And also they didn't influence much on the on the mechanical properties or the elasticity. So particles in the film seem to work quite nicely. Then we'll compared the films with respect to mucin interaction, and we used a very simple setup where we have mucin dispersion on the filter papers, and we put the film in between, and then we measure the forces that takes to detach the mucin and the film. And this is a method with a lot of insecurities. It's very important to pay attention that there is actually what you measure is the detachment between the film and the mucin layer around the filter paper, and not the double-sided tape that holds the filter paper and things like that. So it's not an easy, well, you have to be very, you need to observe closely what you are measuring, what the values are giving you. But when we tested films towards mucin dispersion and towards the unspecific adhesion, that is the same test towards buffer, and then we can calculate the estimated mucin interaction. So there were which you can see in these gray boxes up here, and they are not significantly differing after subtracting the interaction with the buffer. So no impact on putting SLNs in the film on the mucin interaction. We also tried to study the muco adhesion in a model where we had cultivated mucus-producing HT29 MTX cells in 98 well plates. The cells were cultivated for 21 days, and then we measured the amount of the fluorophore adhering to the cell layer after incubation for 1 hour. And we compared a dry film with a film, I mean, it was not an, it was a film, we called it dry because it was used as such, but it was of course mixed with HPSS as a medium during the test. And then we compared it to pre-dissolved film and directly the SLNs. And when the film is pre-dissolved, the SLNs will separate from the film matrix, at least in this setup. So we didn't obtain the muco adhesion that was desired in this test for the pre-dissolved film. But when the film was in the put into the well in dry state together with medium, then we could see muco adhesion. Also, we looked at permeability using the same cell line, and I mentioned that that we should preferably use a cell line of buccal cells in order to look at the permeability that is relevant to the biological conditions. And the HT29 cells, they are from the colon cancer cells, and they are, of course, not the same cell type, but we thought it was interesting to use them nevertheless because they present a mucus layer on top, and we were interested in the permeability with respect also to the mucus layer. There are cell lines that are based on buccal cells, TR146, but they do not secrete mucus. So one could potentially use those as well and then introduce mucus, and that would be a more biorelevant setup. But for simplicity, we use the same cells as in the mucoadhesion test, and since we had varying, it was not straightforward to obtain the same concentration of the fluorescent marker in all wells. So we, the free C6 is a suspension precipitated into the medium from a methanol solution. So this has a very high concentration. And then we looked at the same concentration of the SLNs as we do have in the films, and a 10 times higher SLN concentration. And the flux was not surprisingly much higher when we increased the concentration of the SLNs. But also the flux was higher from the films as compared to the particles as such. Then in another project, instead of SLNs in the films, we used polymeric micelles, and we looked at the Soluplus, which is a grafted copolymer, forming micelles around slightly below 100 nanometers, and they will aggregate at higher concentrations. So we prepared films with only Soluplus, Soluplus combined with other polymers, and for instance with the HPMC. And when we had the combination, the wettability of Soluplus was much increased compared to the pure Soluplus film, which is a solid dispersion, really. And we think this is because of the HPMC pulling more hydrophilic properties to the surface. And then when you have the hydrophilic component there, the dispersion of and self-assembly of the Soluplus micelles starts very quickly. We looked at swelling and erosion, and when the Soluplus was alone, the film eroded very rapidly. When we combined it with the polymer, and the green one here is the HPMC polymer, the micelles were maintained in a network, so they remained there and was not washed off as easily. And this was also studied in a more oral cavity model that we set up, similar to what I have in Copenhagen, but instead of tissue, we used cells, mucus producing cells as the matrix, and they were mounted in a setup in a humidity box, where we flushed over, simulating the saliva flush over the mucosal surface. And then we detected how much of the drug was washed off, and we could see differences between Soluplus and Soluplus in HPMC. So we think that HPMC is maintaining the particles in a network on the mucosa. And also, some results on biocompatibility of the Soluplus and the Soluplus films, again done in the same cell setup. There were some effects of Soluplus, especially when we had high concentrations of solutions. There were not that much effect of the film, which was also seen in the MTT test with the same cells. But the longer the exposure time, the more my cells affected the cells, which is not surprising. We also added as cyclodextrin into these films, and I will go very quickly now because I see that the time is running out for us. But before I stop, we did also we did some preliminary test assessments using an electronic tongue, where we could at least detect differences between the free drug and the drug in the formulation. Well, I hope I've shown you that even though the environment is quite tough for drug delivery in the oral cavity, there are several obstacles that we need to overcome. We think that nanoparticles in mucoadhesive film matrices are promising delivery systems. The film contributes the mucoadhesive properties to increase the residence time on the mucosa, whereas the nanoparticles can offer taste masking, solubilization of polysoluble drugs, or even controlling the drug release. And these are, I would like to acknowledge the students that did the work. Julia and Gabriele did a lot of the studies, and the master students, our engineers and collaborators. And that's all from me and my group. Thank you very much for listening.